So everyone has opened the problem, right? Because I cannot show the problem at the same time. So let's go through the first question. The probability density function of net weight in pounds of a package is based on a function. So, and the function is f of x is equals to 2 for x between 49.75 and 50.25. Determine the probability that a package weighs more than 50 pounds. So this x is the weight of these packages. It's going to go from this lower bound to this upper bound, and the probability of getting any one of these values, not the probability density function is based on this function. Now we want to find the probability that the weight of a package determine the probability that the package weighs more than 50 is the weight of the package. This random variable is more than 50 pounds. Okay, so that's integral of probability density function, right? Integral of f of x dx from 50 to upper bound, and upper bound is this value to 50.25. So that's 2 dx from 50 to 50.25. That is going to be 2x from 50 to 50.25. And when we put the numbers, so it's going to be 2 multiplied by 50.25 minus 2 multiplied by 50. That's going to be 100.5. So the result is going to be 0.5. And this is 100, right? So 100.5 minus 100. So the probability of x, the weight of a package being more than 50 pounds is 0.5, 50%. How much chemical is contained in a 90% of all packages? Meaning that if we want to say with the chance of, for example, 90%.
Professor?
Yes, go ahead.
Usually the videos he do like 1 minus p to x inferior to 50. It's the same, but I don't know which one is good, easy way to do it.
Both of them. So you mean in the video says 1?
Yeah, usually he do that. Yeah, p inferior to 50. So
that's if it was like greater than 50.25.
Yeah.
Here is less.
I see what he's saying. He's saying you could do 1 minus the integral of 49.75 to 50. But yeah, this is easier though. At least you just did it.
I mean, both of them are correct. You can say probability of x greater than
or
50 equals to 1 minus probability of x less than 50.
Yep.
This is, I mean, it's very unnecessary to go. I mean, it doesn't matter. Both of them are, this is integral of 50 to 50.25 f of x d of x. This is 1 minus integral 49.75 to 50 f of
Professor?
X. Yes.
I think if we use the formula that they give, which is like, x minus a over b minus a, we have to do this way. But if you're doing integration, we can use
no. This is not uniform. X minus a divided b minus a is a uniform distribution. It's for continuous uniform. This is not uniform distribution. Here it's just that x goes between these two, and this is f of x.
This is normal random variable, right?
No, this is not normal. This is just a random form. This is 1 over, so yeah, actually, no, this is not normal for sure, because if it was normal, you have to know for the random variable, you have to know average and sigma.
Sorry, I think I meant normal distribution.
Yeah, so if it's normal, For normal, you have to do average and variance. So this is uniform. However, to calculate the uniform random variable, to calculate the probabilities for any distribution, it doesn't matter, uniform, normal, or anything, you can just easily go through the integral as opposed to using the formula. Yes, for the uniform, that goes, okay, let me go here. If X has uniform distribution between A and B, and it's continuous uniform, because we also have discrete uniform random variable, right? If it's continuous uniform, then f of X is 1 over B minus A. And here, 1 over 50.25 minus 49.75 is over 1.5, and it's 2. That's what we have. Now, the probability that the random variable is less than some specific value, it's integral of f of X dx from A to this value X. And if we do the calculation, it's going to be X minus A over B minus A. Okay. Now, if they ask you, what is probability that X is greater than X? You can say, oh, since I know this formula, this is going to be 1 minus probability of X less than X, and this is going to be 1 minus X minus A divided by B minus A. Is that what you are referring to?
That's what I mean, yeah. That's what I mean, yeah.
So that's fine, but you don't need to necessarily memorize the formula. So this thing was calculated by just simply taking this integral.
So I was correct, right? When I said.
Yeah.
Okay. So I have another question, Professor.
Wait, let me finish this.
Oh, sorry.
So I personally, I mean, it's fine to use this formula, absolutely, but I would say that instead of just memorizing so many formulas and things, every time that you have the probability density function of a random variable, if you need to know probability of X less than something, is always going from lower bound to X, f of X dx. Even if you, okay, use the formula, that's fine. If at some point you forget the formula is not available, whatever, this is what always can give you the answer. Probability of X greater than X is probability of going from X to upper bound for this random variable, f of X, d of X. So these two always for any type of continuous random variable, any type, can give you the solution. So these are general formula, and they are safe and reliable, always.
Can you say that again? Continuous.
For a continuous random variable, the ones that we learned in module 4, the uniform and normal. There are actually many more, but the two that you learn are normal and normal and uniform. So both those are in the continuous random variable category. Okay, so so you learn these two distributions. However, in the first folder, you learn just so many about just general continuous random variables, not specific distributions. So general random variables that are continuous, two specific distributions that you learned are uniform and normal. But you learn the formulas, for example, these formulas are applicable to any continuous random variable. You can apply it to uniform and normal as well. The only thing that happened in those videos is that these formulas were applied to uniform and normal, and you saw some final formulations similar to this one. So this is formal final formulation after you apply these general formulas to these random variables, just because you know how the f of x looks like. That's why we could get these final forms, because I know how the f of x will look like in a uniform random variable. But these formulas are general. For any continuous random variable, you can always use. Actually, our second question is like that. So our second question is just a continuous random variable. But if you look at the form of the f of x, if you look at the form of this probability density function, it's not in the uniform category, it's not in a normal category, and that's fine. It's just another continuous random variable. And if I ask you for that, what is the probability of x less than this number or x greater than this number, you just use these general formulations and it gives you the answer. Okay. Okay, what was the other question?
Thank you so
Yes.
much.
Can you go up here a bit, Professor? Here, you said the fx is equal to 1 over b minus a.
Mm-hmm.
But I think it was in modular 2, we learned that like it's actually fx should be 1 over n. In that case, it was like 1 over b minus a plus 1.
Okay, you are okay. So you are talking. Okay, so then that's a different thing.
Yeah, what's the difference between those?
Okay.
That's my question.
Okay, sure. So remember, in module 3, we learned about discrete random variables, right? Discrete random variables. Sorry, in module 2. In module 3, we learned about continuous random variables. And you all know what is the difference between the two, right? If there is one thing you have to learn from this class, that's the thing. Discrete random variables get discrete value. They get value of 1, 2, 3. You can count them. But continuous random variables, you can't count them. They just get, for example, any value between a and b. For example, if I tell you a random variable x is a discrete random variable, and x is between 3 to 7, okay? What are the possible values that this random variable can get?
4, 5, 6.
3, 4, 5, 6,
6, 7.
7, okay?
Mm-hmm.
5 possible values. Now, x is a continuous random variable and varies between 3 to 7. What are the possible values of x?
A lot.
There are infinite numbers in this interval. X as a continuous random variable can get infinite number that goes from 3 to 7. If that's what the whole difference between discrete and continuous. If it's a discrete random variable, it gets only 5 possible value. If it's a continuous random variable in the same range, it gets infinite possible values. Pay attention to that one. So now, let's assume I tell you that x has uniform distribution, and x is also discrete random variable. The only distribution that we have, both the discrete version and the continuous version, is uniform distribution. So x is a discrete random variable and it has uniform distribution, right? And x changes between 3 to 7. Okay, so now what is probability mass function? It's a discrete random variable. We call it probability mass function. What is f of x, which is probability of x equals to this lowercase x, which is a specific value. How do we calculate this? It's equal to, if I consider this as a, lower bound, and this as b, f of x is equal to 1 over b minus a plus 1. Okay? This is f of x, which is probability of x equal to something. That's my probability mass function. If I tell you x is actually uniform, it has uniform distribution, but x is a continuous random variable. And x, again, changes between 3 to 7. Okay? Then, what I'm going to, then f of x is called probability density function. And it's called probability density function. And f of x, if I want to calculate it, is called 1 over b minus a, which is 1 over 7 minus 3, which is 1 over 4. Okay, so so that's the probability density function, which for x, if it's a continuous random variable and uniform distribution, probability mass function if x is a discrete random variable and has uniform distribution. For example, for this specific problem, f of x is going to be 1, 7 minus 3 plus 1 is going to be 1 over 5. If x was discrete. And one very, very important thing, again, if you take one thing out of this class, this also should be one of those. If assume x is a continuous random variable and has uniform distribution, what is this probability? Probability of x equals to, let's say, 4. Okay, I want to know this, and I have the same question here for the discrete random variable. I also want to know that for this discrete random variable, what is probability of x equal to 4? I want to know the answer to both these questions for x continuous random variable and x discrete random variable. Both of them have uniform distribution. First, give me the answer for the discrete random variable. What is this probability? Probability of x equals to 4.
1 over 4.
1 over 5.
1 over 5.
Oh, yeah.
1 over 5, because we said all these possible values that x can get, 3, 4, 5, 6, 7, all these 5 values, all of them have the same probability of x equal to something, x equals to 3, 4, 5, 6, 7, 4 here. All of them are going to be 1 over 5. They have the same probability of happening. Now, assume x is a continuous random variable. Tell me.
0.
0.
Yeah.
Because always you need to be
Perfect. Now I understand.
unfair.
Okay, so this is, guys, if in in one of the exams, I give you a question like this for a continuous random variable and you don't say 0, you are going to fail.
Why?
Because if you leave this class and you don't know the answer to this, that means you didn't learn anything. So for a continuous random variable, always probability of x equal to something is 0, no matter what type of random variable it is. It's uniform, normal, exponential, any random variable. As long as it's continuous, this always holds. But if it's discrete, this has a valid number and you just have to find it. Okay?
Professor, if it was px less than 4,
then it has a value.
it has 1 over 4, for example, on this case, or?
Okay, so let's do the calculations for both again. Okay, x discrete, probability of x less than 4. We want to calculate that, and then for x continuous random variable, I want to calculate probability of x less than 4 too. Okay. No. Before I do the calculation, first of all, for a continuous random variable, can I write this as probability of x less than equal to 4? Are these two equal or not?
Yes,
Because
x equal 4 is 0.
x equal to 4
Is
equals
0.
to 0 in a continuous random variable. So it doesn't matter if you put the equal sign or not. For example, if I ask you, what is probability of x between, let's say, 3 and 5? This is equal to probability of x between 3 and 5. This is equal to probability of x between 3 and 5. This is equal to probability of x between 3 and 5. So it's the same for all of them. It doesn't matter if we put the equality sign or if we put it in one of them. It doesn't matter. All of them are equal. All of them. In a continuous random variable. Again, this is very, very important, guys. Pay attention to that. For a continuous random variable, all of these are the same. However, if x is a discrete random variable, how about this? Can I say these two are equal? Similar to what we have for a continuous random variable?
No.
No.
What are the things in, so when I say probability of x less than 4, so x is between 3 to 7, similar to previous example. So what are the possible values that we think x can get?
Just 3.
X equal to 3. How about this one?
3 and 4.
3 and 4.
So that's 105, or that one is.
Exactly. So these two probabilities are not equal. Always probability of x less than 4 compared to probability of x less than to equal to 4 is always less than or equal. And this is always for continuous random variables. Okay. So keep that in mind as well. The equality sign in these probabilities make a huge difference for discrete random variables, but for continuous random variables, they do not. For discrete random variables, probability of x equal to something has a valid value. For continuous random variable, probability of x equal to something is always, 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 always 0. Good? Now, okay, so if I want to calculate probability of x less than 4, is there a question? Guys, I don't, is it a question or you're not on mute? Because
Sorry about that.
No, it's okay. Okay, so we want to we assume x has continuous distribution between 3 to 7, and I want to calculate probability of x less than 4. Okay, if it's continuous random variable, always, always, always these
Integration by.
Exactly. These rules are the ones that we have to go with. Always integration from either lower bound, depending on the is less than or equal or greater than or whatever.
So we need more information in this case.
Why?
Or the fx will be 1/4.
F of x is here.
Okay.
Yeah, actually. Yeah. So here, that's the one I calculated, right? Here. F of x, exactly, is 1/4. So x is continuous, x is uniform between 3 to 7. So integral of f of x, d of x, less than 4 means from lower bound, which is 3, to value of x, which is 4, f of x, which is 1/4, d of x, because we calculated f of x here for this continuous uniform random variable between 3 to 7. And that becomes x over 4 between 3 to 4, and that's going to be 1 over 4. Okay? Now, if x is discrete random variable and continuous random variable between 3 to 7, we just said f of x equals to 1 over b minus a plus 1, and it turned out to be 1 over 5. So if I ask you what is probability of x less than 4, that means basically only probability of x equals to 3. And that's 1 over 5. If I ask you probability of, if it's in the continuous scenario, if I ask you probability of x less than or equal to 4, that's still the same value. It's 1 over 4, because these two are the same. In a discrete scenario, if I ask you probability
You
of,
mean x discrete, not continuous?
sorry, so for this one, it's continuous.
Okay.
For
the bottom one, you put discrete continuous.
Yeah, this is wrong. Just you
sorry,
type in this one.
sorry,
Yeah,
I meant
thank you.
uniform. Thank you.
Yeah, no problem.
Uniform. Although Lakers won, I still make a mistake. So
Yeah, I was confusing with it.
no, sorry. So that I meant uniform. So x is discrete and uniform. This was the formula. That's what we did here for this random variable, and probability of x less than 4 means probability of x equal to 3, which is this. And in this scenario, if it's continuous, probability of x less than 4, probability of x less than or equal to 4, all of them are the same, 1 over 4. But if it's discrete, probability of x less than 4 is different from probability of x less than or equal to 4. It's probability of x equal to 3 and
Plus.
probability of equal to 4. That's 1 over 5 plus 1 over 5. And that's 2 over 5. Or in other words, for the discrete random variable, remember, instead of integral,
summation.
The example is just summation. Sigma. Oops. Is summation.
Thank you, Professor. This has helped a lot.
Of course, that's the whole point of the. So
yeah, I was just confusing with lots like.
I know this class is one of the craziest classes on time.
Like chapter 2 by himself is fine. Chapter 3 by himself is fine, but combining together, I was confused, but now it's perfect.
Oh, good. Yeah. So when I did my undergrad, we actually had one full class, 3 unit for probability, which was the concepts that we learn right now in module 1, 2, 3, and 4. And then we had another unit, another 3 unit class, which was the statistics. And that is basically the rest of the modules that you learn in this class. And now we have to teach both of them in one class. It's a lot. So I know how you guys feel. It's a lot of material. And it's a very important class because no matter what you do, where you go in industry or academia, you always will work with the data. And it's always about how to report the numbers, what makes sense. And you have to know these concepts. Anyway. Any question?
Perfect. Thank you.
Sure.
Professor, will you usually be told if it's discrete or continuous? Right?
Yeah. Yeah.
Okay. Thank you.
Yeah. That's something in the problems. For example, if it's uniform, for sure you will know, because uniform, as I said, is the only distribution that we have both in discrete and continuous. However, for example, if I tell you X has a normal distribution, blah, blah, I'm not going to tell you it's continuous anymore. You have to know a normal random variable is a continuous random variable. If I tell you X has binomial distribution, blah, blah, I'm not going to tell you X is discrete random variable. You have to know a binomial random variable is a discrete random variable. But if it's something like, if I tell you, oh, f of X is 2 to the power of blah blah plus.
This is continuous.
Yeah, it was just give you an fx, which is not a specific distribution, then I tell you it's continuous or discrete and things like that.
Okay.
But if they are specific distributions, no, you have to know what distribution is continuous, one distribution is discrete. If it's uniform, since it has both continuous and discrete, I tell you which one we are looking at.
Okay, sounds good.
Good. Okay. Okay, we haven't even finished question one.
That's perfect. Believe me, we don't need the question one.
No,
This is make our stuff like put them in order now.
No, sure, that's good. Okay, how much chemical is contained in 90% of all packages? That's part B of question one. So that means if I tell you that this random variable x, which is the weight of these packages, is greater than a specific number, we want that probability to be 90%. Meaning that if I know this specific weight, I can say by the chance of 90%, every package has a weight greater than this number. Okay, it's important for you guys to know how to write questions like part 2 in the form of probability so that you know what you have to calculate. So, okay.
Are we looking for Z now or something?
No, we are in question 1, part 2, and this random variable has, remember, x, f of x equals to 2, and x is between 49.75, 0.25, and we just said that x, since it's equal for every number in this range, it's like a uniform, right? That's the whole definition of uniform. Uniform random variable, no matter if it's continuous or discrete, means the probability of all possible values are the same. And that's exactly what happens. The probability density functions are the same. Probability mass functions are the same. So that's why we said f of x, if this is A and this is B, f of x equals to 1 over B minus A, and B minus A here, if we calculate, is 1 over 0.5, and that's 2. And that's exactly what we have here. So this is a uniform random variable. Z concepts is only for normal random variable. That's only for normal. Okay. So now, if I want for this random variable, I want to calculate probability of x greater than some. So I want to find this x value. So probability of x greater than x equals to 0.9. So that's integral of greater than x going from x to upper bound. And this is the upper bound, 50.25. F of x, which is 2. D of x, that's going to be 2x from x to 50.25. That's 2 multiplied by 50.25 minus 2x. So this is a number I have to replace instead of this x. So that's basically 2x. And this, I want it to be 0.9. So the question is that, what is the value of x? So if you solve this, it gives you the value of x that can satisfy this probability. So any package that has a weight greater than this, or any package with chance of 90% will have a weight greater than this number. So that's how.
So
so x is 49.8.
Thank you. What was the question, guys?
I thought we have to do like 49.75 to x.
How much is contained in 90% of all packages? Why going from that? Mm, you mean
Yeah, on the video examples, I'm pretty sure they did it like this. They set x equal to the lower bound, and then they went to the upper bound, and then put the probability on the right-hand side of the equation.
like the one I did, right?
Yeah.
Okay. Yeah, that's how it should be do. How much is contained in 90% of all packages? Meaning that with the chance of 90%, you can say the weight of this package is greater than something.
But then, if it's 90%, you can still go with you can still start with the upper bound. I mean, the lower bound, right, to the x. So how do we know when to use the x in the lower bound or the upper bound?
Let me think.
Yeah, it's a very simple geometry that's a rectangle, and you can move that rectangle around wherever you want, up or down, and still get the same result. But when I plug in the two different ways of doing it, I get 49.8 and 50.2.
Yeah.
So I guess it goes.
Yeah, because they didn't specify if it's greater than or less than
But it's saying like the 90%, so I assumed like the first 90%.
How do you know?
But yeah, my English is not good, so I don't know.
English is my second language too.
My third language, so I'm like, that's my worst, like, that's my problem.
Oh, no worries. So what chemicals contain in 90% of water? So maybe this question should be a little more clear of what is the, for example, the value where we can say 90% of packages have less than that weight, or 90% of packages have greater than that weight. Maybe that's how this question should be. If I say what should be the weight where we can say 90% of all packages have less than that weight, then is probability of x less than or equal to x is 0.9. If I tell you what should be the weight such that 90% of packages have a weight greater than that number. So yeah, so probably this question should be a bit more clear. I see that how we can go both ways. Yeah, so let's consider it that way. So if we have, what is the probability that, what is the value of the weight? Oops. What is the value of the weight for a package where we can say 90% of the packages has a weight less than this number? We're going to write it as that. Then what is the weight of a package where we can say 90% of packages has a weight greater than that? We are going to write it like that. Okay.
Yeah, that makes sense.
If I see, I continue thinking about it in this today. If I see anything like get to any different point, I'll let you know.
Well, the exam will be together, so we can ask questions, right? To clarify like stuff like this.
Yeah. So if for the exam,
perfect.
I will for the exam I will make sure that the questions are very, very clear. No worry about that. Yeah, but here I can see that we can go both ways. Okay. So, okay. So let's go to question 2. Any question, guys? Can we go to question 2? Good.
Yeah.
Okay. The distribution of x is approximated with a triangular probability density function f of x equals to this for x between 30 to 50 and x equals to this for x between 50 to 70. What is probability of x less than whatever? So for this, we say, okay, so f of x here, I think for all of the examples we have had in the videos or homework or quizzes, always f of x was equals to one functional form, but here f of x actually gets two functional forms. One of them is this, when x is between 30 to 50, and one of them is plus. When x is between 50 to 70. Okay, so, and that's perfectly fine. We always had one of these functional forms. We always had, for example, f of x equals to this, then x is blah, blah, but it's fine. If x gets two different functional forms for x between two different, in two different ranges, that's fine. In this scenario, x is a continuous random variable for sure. Okay, we are basically in module 3, so we are working continuous random variable. And x goes, the lower value, the lower bound is 30 and upper bound is 70. But instead of just having one probability density function for all these values, it has two forms for probability of density function. When
combining.
X is between 30 to 50 is this, when x is between 50 to 70 is this. So now the question A1 says, what is probability of x less than or equal to 40, right? So what is probability of x less than 40? So x40 is in the first range, right?
So we're using the function first, okay.
Exactly. So first of all, this is all, we all know this is equal to this, right? They are the same. I'm just writing it so that you guys, this becomes like
Because p to x equal 40 is 0.
yeah, so I want you guys to just get used to this. So anyway,
For the function of n right there, is that supposed to be 0.175 or 0.075?
Yeah, one is, yeah, is right now 175.
Let's forget the board file is yeah, I think.
Yeah, you're right. The professor is right.
It can be 0.075.
I don't know what happened, guys. What is this? Stop. What did I do?
You forgot to charge your pen again.
No, it's 100%. See, 98% on the top. Okay, let's talk about Lakers championship while this is getting fixed. What is going on? Please stop.
Was it a good game?
It was great. Friday they did horrible and they lost, and I was so stressed for the Sunday game, and I thought I'm not going to watch. This is going to go to game 7. They are going to lose again, and then I realized I cannot not watch. So I started watching it, but they played so defensive and they did such a great job. Anyway, like, let me close this thing. Wait 1 second, let me fix this thing and see what's going on. Okay, fix. Okay, okay, sure, good. Okay, what we want to calculate is probability of x less than or equal to 40, which we know is equals also to probability of x less than 40. I just want to mention this so that you guys get used to it. So probability of x, so x40 is, we said, is in the first range. So if I want to calculate this, since x is a continuous random variable, it's always integral from lower bound, which is 30, to the value of x, which is 40. F of x, which is this, for x equals to 40, for x in this range is at the first function, 0.0025x minus 0.075
P to X.
So just do the calculations. Whatever you get is probability of X less than 40 or less than or equal to 40.
0.125.
Whatever you say, I accept that. I'm not going to, I'm just lazy to write that number. But you have done the calculations before?
Yeah, I got the same as him.
Okay. So repeat one more time, 0.125. 125. Okay.
Yeah, 1/8.
Yeah. Okay. So now we want to calculate probability of X between 40 to 60. Okay. For this one, X, we know that X between 40 to 50 falls in this range. X between 50 to 60 falls in this range. So I have to then write my probability as
We divide them.
exactly from 40 to 50.
F the X1.
5x minus 0.075 d of x
And from 50 to 60.
bracket plus probability of from 50 to 60 minus 0.0025x plus 75 dx. And if you calculate that, you find this probability. So in other words, I say that probability of X between this, since X is in two different range and gets different value, different probability density functions, I can write it as probability of X between 40 to 50 plus probability of X between 50 to 60. Right? And that's exactly what these probabilities are. Good. Next, part 3, what is the value of X that is exceeded with probability of 0.989?
For the answer, is that less than or equal to, or is it just less than?
Which one?
Wait, for the answer, in the green, the second part, plus P 50, yeah, right there.
Does it matter?
No.
No. Then you answered your question. For continuous random variables, it doesn't matter. I can put the equality sign for both. It doesn't matter. Or I can just say probability of 40 less than X less than 50 plus.
Yeah, because if they are continuous, doesn't matter.
All of these are the same. It's continuous random variable. The equalities do not matter. Part 3, what is the value X that we exceed with probability of 0.99? Probability of X gets greater than X equals to 0.99. Okay. So since this, so everyone can get the same thing by reading part 3. It's not confusing here. Although it could be written better, but at least it says what is the lower value of X that we can exceed with probability of 0.99. So then this is how we have to write it. Okay, it's not as confusing like the first question. So since it's 99%, so it's probably somewhere in the lower, in this range, because anything greater than that is 99%, which is pretty much all, like the whole probability from the lower bound to the upper bound. So then I would say this is probability of X to 50, 0.0025 minus 0.075 dx plus probability of 50 to 70 minus 0.025 dx. And this is going to be 0.99. If you calculate the integrals, put it equal to 0.99, then you find the value of x that can satisfy this condition. Okay. Now.
So in other words, it's asking like, what is the number x to 70 to be 99% of our solution?
So what is the value of x that the random variable can exceed that value with probability of 99%? The random variable can exceed this value with the chance of 99%. Any value that we pick for the random variable exceeds this value, is greater than this value with a probability of 99%. Okay. Part 4, what is CDF? CDF stands for?
On CD,
So distribution function.
Cumulative.
Cumulative.
CDF, how much is it?
Cumulative distribution function. So if my f of x has two forms, then my CDF is going to have two forms too. So CDF, if x is any value between 30 to 50, then I need to calculate the probability of x less than or equal to lowercase x, and also if x is between 50 to 70, I still have to calculate this. Okay. So now let's see how we do this. CDF equals to integral,
Yes, it is 30 to x, the first one.
Yeah, so from lower bound, which is 30 to x,
The x, f the x.
0.0025x plus 0.75 d of x. Whatever we get from this.
And the other one would be 50 to x again.
Yeah, so this is for any x between 3 to 50. However, okay, so how about here?
From 50 to x.
So here, basically, it says, what is the probability that x less than x? And okay, so for example,
I think we have to put 0.5 plus that, because the solution for that from 30 to 50 is...
yeah. So what is probability that x is less than or equal to 60? So the probability that x less than or equal to 60, all of these values are in that probability too, right? X less than or equal to 60 is not just between 50 to 60, is from 30 to 60, right? So for the second one, if I want to calculate the probability density,
Okay, I got it now.
I have to say it's integral. First part, 30 to 50.
250 plus, yeah. Because it's continuous, that's why.
Yeah. Plus
X.
from 50.
I think from X to 70.
50 to X.
Are you sure?
Yeah. X, if X is less than 60, that's what we want to calculate. What are the values? From 30 to 50, which we have in the first one, and then from 50 to 60. From 50 to this value. And the second function, which is minus 0.0025x plus 0.15 d of x. Remember, CDF is always probability of x less than or equal to x. So this is always upper bound, like here or here. Okay. So if you calculate these two and add them together, then that's the CDF for the time when x is between 50 to 7. Does that make sense?
Yep.
Okay. Question 3. Can I go to the next page, guys? Did you take note, everything?
I don't.
Professor, you're
I'm
going to
good.
be posting this video, right?
Yeah, that's the whole, yeah. It's recording, right? Yeah, it's
Yep.
just. Mhm. All good? Next question?
Yeah. Thank you.
Next. The volume of the shampoo filled in a container is uniformly distributed between 374 and 380 millimeters. So X has uniform distribution between 374 and 380. For example, here it doesn't tell you it's uniform or continuous. I mean, since the question is obviously for module 3, it's continuous, but in the exam, I tell you for uniform, I tell you if it's continuous or discrete. For the exam, I'll tell you only for the uniform. However, in the real world, if you had a situation like this, I would look at the problem context. I would say it's the volume of a shampoo, right?
Something is, yeah, it's hard to count it.
Yeah, it's a continuous
Mm-hmm.
texture, you know. So it makes sense. It makes more sense for X to be a continuous uniform. If I tell you, oh, the number of students I have in a class is between 35 to 40, any one of
That's
them can have that.
discrete.
That's discrete because
Mhm.
number of students is what, like 35, 36, 30, you can count, right? So in the real world, if you deal with situations when you know it's uniformly distributed, but you don't know if it's discrete or continuous, think about the context and which one makes more sense. In the exam, I'll tell you if it's uniform, and that's that.
So, Professor,
Go ahead.
question number 1 was uniform. Question number 2 was not uniform, right?
Yeah, it's just question number 2 is just a random variable that has continuous distribution.
Okay.
That's what it
Okay.
is. Because remember, we have random variables that are discrete or continuous. Some of those have some specific form, and those forms fall in the category of those distributions that you have learned. Some of them are discrete and have uniform distribution. Some of them are discrete and have binomial distribution. Some of them are discrete and have negative binomial. Some of them are just discrete, but they have a functional form, f of x equals to blah, blah. It doesn't fall in any one of those distribution categories.
Did we learn binomial?
Yeah.
Okay.
And you learned binomial, but you didn't learn negative. I think you didn't learn negative binomial. I'm not sure. I have 3 statistics classes.
We just do binomial and Bernoulli.
Oh, you learned, you learned Bernoulli and binomial.
Yeah.
You didn't learn the negative binomial. The other class learned negative binomial. But anyway, these distributions that you guys are learning in this class just are 2 or 3 of tens of distributions that are out there, right? Obviously, you're not learning everything in this class. But the same for continuous random variables. Variables can have continuous distributions, or they can be continuous random variables, but only some of them fall in those categories that we learn: uniform, normal. One other thing that you will learn in module 4 is exponential. But if there is one, like the one in question 2, that doesn't fall in those categories, that's fine. It's still all of the rules we learn generally for continuous random variables apply to them, right? Okay, let's go to question 3. Okay, the volume of shampoo has uniform distribution between these two values. What are the mean and standard deviation of the volume of shampoo? Expected value of x, we know, right? What is the formula? If it's uniform, and this is A, lower bound, and this is B, upper bound, what is the formula? A plus B divided by 2, right? 374 plus 380 divided by 2, and I believe that's 377. What is variance of x?
Is b minus a square over 12.
12. Yeah. 380 minus 374 squared divided by 12, and I think it's going to be 3. What is the probability that the container is filled with less than the advertised target of 375?
Is
There's a
p
value that
x
the weight of a container,
less
volume of container is less than the advertisement, which is
375.
And that's from lower bound, which is 374.
375.
To this 375. F of x, which is 1 over
b minus a
e minus a
dx.
dx. And this f of x basically is going to be 1 over 6, right? This f of x is basically 1 over 6.
Yep.
So do the calculation. So basically it's going to be actually 1 over, when you do the calculation, it's going to be 1 over 6 at the end. What, part 3, what is the volume of shampoo that is exceeded by 95% of the containers? Okay, this
That means
one.
bigger. X is
Yeah.
bigger than x.
Exactly. So this question is clear. What is the volume of shampoo that is exceeded by 95% of the container? The weight of this container exceed this value 95% of the time.
Let's see. Is
Is integral of x to upper bound
375 or 380. Sorry.
d of x, and that's going to be 380 minus x over 6 equals to 0.95, and just do the calculations. Whatever you find for x, it's a value, it's the volume of containers such that 95% of the containers volume exceeds this value. Okay. For every millimeter of a shampoo costs the producer $0.002. Any shampoo more than 375 millimeter in the container is an extra cost to the producer. So if we have any container that has a weight greater than 375, for every millimeter greater than that, we are going to have this much cost. What is the extra cost for a shampoo, for a container? How do you think we have to calculate that? What is the average extra cost for a shampoo?
The mean, we are looking for the mean.
Yeah, so we say that we don't know exactly what is the weight of each container, but I know on average, the weight of a container is what we calculated here, is 377 millimeter, right?
Mm-hmm.
That's average weight of a container. Anyone that we picked, on average, we expect to see this weight. However, the target is 375, and for any millimeter greater than that, we are going to have this much cost. So then the cost of a typical container that we pick is going to be 377, which is the average weight of the container.
Minus 375.
Target, which is 2 millimeter, multiplied by this dollar thing. That's going to be $0.004 cost on each container in this system. Average cost of each container in this system. Good. And then question 4. An electron emitter produces electron beams with the energy level that is uniformly distributed between 3 and 7. Suppose it's possible to adjust the upper limit of this energy beam. So the level of energy of these beams is a random variable, which has uniform distribution between 3 to 7. And what is the mean? We just calculated that. We are not going to repeat. A plus B divided by 2. This is A. This is B. What is variance of this? I'm not going to
5.
repeat it. Yeah, so here average is 5. The variance, you know how to calculate it. We just calculated that for this one. B minus A to the power of 2 divided by 12.
That's 16 over 12.
Whatever. Is it 16?
B minus A over square over 12.
2, 16, yeah.
16 over 12, this means 4 over 3.
1 over 3. Okay. What is the probability that an electron beam has a kinetic energy of exactly 3.2 joules? What is the probability that the beam has an energy level that is exactly 3.2 joules? The energy level is our random variable. What is the probability that the energy level is exactly 3.2 joules? All of you say it together.
This is 0.
0.
Yay.
Okay, so this is 0. What should be the upper limit so that the mean energy increases, the mean of the energy increases to 8? So apparently this upper level can be adjusted or can be changed. It says what should be the upper level such that the mean of the energy of these beams is going to be 8 joules. So what should be the upper level? What should be the B such that the average is 8? So expected value of X equals to A
Plus B.
It's between 3, but we don't know what should be our upper bound such that the average, which is A plus B over 3, which is, over 2, which is 3 plus B over 2 is
Equal 8.
8.
That's 16 minus 3 is 13. Yep.
And B is 13. And then part 5 says what should be the upper limit so that the variance of the energy decreases to 0.75. So again, we want to find for this X, we know the lower level is 3. We want to find the upper level such that the variance of X this time is 0.75. And variance is B minus A to the power of 2 divided by 12. It's going to be B minus 3 divided by 2 to the over 12. This is going to be 0.75. And if you solve this, you get the B, the upper limit, that is going to give us this variance as opposed to 1 over 3, which we found.
Professor, I have a question.
Yes. Yes.
Oh, the variance. I don't know what means variance. I know what this means, but like, what do we use it for?
So let's say I tell you.
Because the mean, that means the average of the.
So let me tell you this. So let me so this is just a general scenario. So I tell you that I measure, let's say, the weight of the students in Cal Poly Pomona, and so the numbers are, let's say, 130, 135, 120. Like I can also get things like 180, 190, and I can also go to maybe 80, 90 pounds, okay? And then let's assume I calculate the average of these numbers, and I find out that the average is 30 pounds, okay? And then for another school, I'm going to do the same. I'm going to get a sample. I may weight these students, and then the weights are going to be anywhere like 130, 140, blah, blah. And maybe I go up to 155. And then from here, maybe I go up to 100. Okay. And I do the same. I take a sample maybe of size 100 here, and I do the same. I take a sample of size 100, and these are the weights. And again, I calculated the average of all these people that I weighted, and the average is again 130. So now let's assume you are doing this analysis for a public health department of LA. And they wanna, let's say these two schools are at two different places, and they expect that schools in this neighborhood A, because of some environmental issues, people have higher weight, and in the environment B, because the environmental situation is better, people have better weights. So you have taken a sample from the school in environment in the neighborhood A. You have taken a sample of size 100 from the school in neighborhood B, and you report to the public health department in LA that, oh, the average of both samples is actually 30. So I think both schools are doing good. So they are the same. There's no difference. But is that a valid report?
No.
Because?
One school can have really high people and then really low people, and their average would be 130.
Exactly. So if I only go ahead and say, oh, average of the first sample is 30, average of the second 130, and average of the second sample is 130 as well, and actually the weight of the students in both schools are the same, I don't think the environment matters at all, and I'll publish a paper on top of that, that's the wrong report. I not only have to write the average to report the average of this number, but also have to report the spread around the average. If in one neighborhood the average is 130 and all of the numbers are around this average, that's good. But if in another school average is 130, but it can go as high as 190 or 200 or as low as 80 or so for school level people, that means the environment actually has affected the weight of people. There is malnutrition which causes people to have lower weight. Some people have like, I don't know, overnutrition, like, or just eating very, very unhealthy. That's why they gain all this weight. So I shouldn't just rely on reporting the average. I also should report some measure of the spread around average so that we know how this average is reliable. If the spread around average is too much, this average is not reliable. If the spread around average is not too much, the numbers are very narrow, then this average is reliable. You can say, oh, these setups for this environment, for this neighborhood actually make sense. Why don't we make those changes here as well? So variance gives you that measure. Variance gives you the measure of spread around average. That's why the variance is x minus average to the power of 2, and then add them, blah, blah. So the formula. So you look at the spread around average. You have the average, you find out how each x is different from average on both sides. If this spread is big, your variance is big. If this spread is small, your variance is small. So small variances are good. Small standard deviations are good. That means small variability in the random variable. Does that make sense?
Thank you so much.
Of course.
And if it's 0, that means everyone is 130, right?
Yeah, if it's 0, that means there is no, if variance is 0, that means you don't have a random variable even. Like, it's not random. It's just everything is exactly 130. There is no randomness.
Okay.
Variance is always, for random variables, variance is always greater than 0, but it's just a matter of how big it is. If it's just too big, too much variability. Like for example, if you're reporting something at your work, for example, you guys are civil engineers, right? So let's say someone asks you, help me with the schedule of a construction project. And then you go to find out, oh, okay, what are the tasks that happens here? And then you want to get some numbers for the length of these tasks. How long would they take? And then you go look at previous projects and you get some samples from the length of task A, right? So, and then you look at the average. So let's say you look at 20 previous projects and each one of them gives you a number for the length of task A. And then you calculate the average of them and say, okay, I'm going to put average of 25 days, for example, for task A. But that's not enough. You also have to look at the spread around this average. If the average is 25, but this task has gone anywhere from 2 days to 100 days, you cannot trust this number. What if the 100 things happens in your project? It just pushes everything around. But if you look at the average is 25, and the variance is small, then it shows, oh, this average is reliable. Maybe most of them are around 25, and it has gone anywhere between 22 to maybe 28. Then this average is reliable. You can use it and you can put it in your project plan and rely that. So your total project length is not going to suddenly get doubled because the estimate of your average suddenly became 4 times of what you estimated. Okay, so always for random variables, we not only want to report average, but also we want to report a measure of spread around average, and variance or standard deviation gives you that measure. Good. Okay, let's go. Okay. So most of what we did right now were for uniform, right? If it's normal, for normal random variables, they have some average and some variance. There is nothing hard about normal variables. If you need to calculate probability of X greater than something or less than something, how do you calculate that? Guys, you learn.
You're talking random and continuous.
Yeah, normal is always continuous.
Okay.
X has normal distribution with some average and some variance. So,
and what are we trying to calculate?
Probability of X greater than some number.
Oh, I see. Okay.
Which is the
we do 1 minus
1 minus P of X.
P of inferior to
why
0.
Why do you need to do 1 minus?
Because it's normal.
Oh, I see.
Okay, so let me put it. So since it's normal, we always have to transform normal to normal standard, right? Because if it's normal, right? Like a typical formula for a continuous random variable, I have to say integral from X to upper bound, which we know for the normal is infinity, f of X, d of X, right? And f of X for a normal random variable is the crazy function 1 over 2 pi sigma e to the power of blah, blah. It's a crazy function, right? We don't want to do this integral. So someone has done all of these calculations and they have given us the Z table. So for a normal random variable, only for a normal random variable, if you ever wanted to calculate the probability, all you need to do is to transform it to standard normal, right?
So the Z is only for continuous, yeah?
Only for normal, so not every continuous, for normal random variable. A normal random variable is always continuous. There is no discrete normal random variable.
Okay, thank you.
So the Z, the transform into normal standard, is always for a normal random variable. So how do we transfer to the z? We say x, we deduct the average divided by the standard deviation greater than x minus average divided by standard deviation. Okay, and this left side is basically what we call as capital Z, probability of Z greater than x minus average, which is, okay, let's make up something. I would say x has normal distribution, average 10, variance 4. X minus 10 divided by standard deviation is?
I can't see the standard deviation. The screen is.
Oh, there you go. Is a root of the 10? No, 4.
Root of 4, so 2.
Or 4.
Exactly, 2. So I need to calculate this, and this is what I call as lowercase v. So I have to then find this property, and to be able to find this probability, I have to go use
the table,
z table, okay? And that's all good. However, pay attention. If you look at your z table, guys, go open your z table. Let me. Okay, so let's assume I have asked you to calculate probability of that the x greater than 12. Remember, so let's assume this is what I asked you guys to calculate. Probability of x greater than 12. So then this is 12. The lowercase is 12, right? X minus average divided by standard deviation is z, and then (12) minus average divided by standard deviation, and that's what I have, minus 10 divided by 2. Okay, and that is probability of z greater than 1. Is everyone okay so far?
Yep.
Clear what is happening?
Yes.
Okay, so this is what I want to calculate. Now let's go open the z. Let me open that as well. I'm going to stop this because I want to stop. I want to share my z table. Okay, everyone can see my screen, right?
Yes.
Okay, so this is my z table, and what I want you guys to pay attention to is that when you look at the top part of the z table or in both pages for z positive or negative, it says the probability that is given in the body of the table is probability of z less than this lowercase. It's probability of z or random variable less than this value. Okay, so this is what we get from the table. However, in the problem that I solved for you guys, what do we need at the end of the day? Did you take note?
Bigger than. It was bigger than 1, so we have to take.
I need probability of z greater than 1, and if I just go to 1 and say, oh, this probability, that's not that. This is, if I just get this value.
Almost 2.
Yeah, so this, give me 1 second, guys. If I just go to the z table and find and just get this value, I say, okay, z1, oh, that's 1. So this number, and just report this number. This is probability of z less than 1. That's what this number shows. What is the probability that z is less than 1? But what I want in this question that I gave you guys is probability of z greater than 1. So what should I do then?
1 minus p to z and for each to 1.
Exactly. So then probability of z greater than 1, I'm going to write it as 1 minus probability of z less than 1. And probability of z less than 1, I'm going to get the 1 from the table, and this is that probability, which is 0.84.
Oh, okay.
So let me just stop it one more time and just share this thing. Where is it? Okay. So since the table is giving me this, I'm going to write what I want into this form such that I can get this from the table, and that was 0.84, right? And whatever is remained is the probability. Give me 1 second, guys. It's just going to answer. Don't worry. No, class. Don't worry. Okay. Is this clear, guys?
It's clear, yeah.
Mm-hmm.
We had a homework problem like this.
Yeah, that's good. So just make sure to pay attention to what the Z table shows. It's always, the ones you have is always this type of probabilities. So that's what we get. And
So this is no standard normal random variable where we use z.
Z, yeah, Z is the standard normal. What do you mean?
Well, we started with a normal, and then
Yeah,
she transformed it to this.
The one that we started with
Is okay.
any normal. So any normal random variable can have some average and some variance. These are the notations you guys used in the video, right?
Mm-hmm.
Yeah. So any random variable that is normal has some mean and some variance, and that's absolutely fine. Only the normal standard random variable is the one that has mean mu 0 and and variance of 1, and we have the Z table for these values. So I can from these I can get probability of Z less than any value from minus infinity to plus infinity from the Z table. However, it's just only for this type of normal random variable. That's why for any other normal random variable, first I transform it to Z such that I can use Z table and find the probabilities that I want. Does that make sense?
So what's the difference between normal and like the other stuff that we're doing like in chapter 3? It's the graph. It like the normal graph, it's equal. The other one's not gonna be equal if we're gonna try to graph it.
No, they are. So the ones you learned in chapter 3, they are discrete random variables.
Let's say continuous random variable.
The ones you learn in chapter 4.
Okay, yeah, I mean modulus 3. Yeah, chapter 4.
So the difference is exactly the shape. So for example, for a uniform random variable, when we say that it's good between A to B, it means this is the shape. All the values between A and B have the same chance of happening. Okay?
That's the continuous. So
that's the uniform.
Uniform, okay.
Uniform. If this is f of x, this f of x is the same for anything between A to B. This f of x is the same. If this is the random variable that is made, like obviously it's not going to be between A and B, but if this is normal with average, let's say A, normal with normal with this average, let's say A, then the shape of the probability density function is like a bell shape, like this. This is how a normal random variable would look like, which means what? Which means for a normal random variable X that has normal distribution with average A and some variance, the values around average have higher chance of happening. And if you get too far from the average, like
So
here.
the uniform also has average and variance, yeah?
Yeah, so it does have, but here the all these possible values have the same chance of happening, as you can see.
Oh, okay, I got you.
But in the normal random variable, the values around the average have higher chance of happening, as you can see here. As you get far from the average, the values have lower chance of happening here.
What's the continuous random variable? Like the graph will be completely off every single example, or it can be triangle and
No, for the continuous random variable.
yes.
So yeah, for the continuous random variable, these probability density functions are continuous, are connected. So if it's a discrete, for example, for a discrete random variable, if it's uniform, this is how it's going to look like, the probability density function. But if it's discrete between A and B, then let's assume these are the values, then the probability mass function is like this. That's your probability mass function. So this
is still uniform, right?
Yeah, this is still uniform. And as you can see, since it's uniform, all the possible value A plus 1, A plus 2, blah, blah, have the same value for the probability mass function. They're all the same. However, it's not continuous. It's just this, 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 this. But for a continuous random variable, since between A and B there is infinite numbers, if you want to specify this for all of these infinite values, it's just going to be a line as opposed to this dot, point, which are the probability mass function for this uniformly continuous, uniformly discrete random variable. Good. With that, we are done with these practice problems. Make sure you guys are comfortable with the quizzes, with the homework, with the examples in the videos, with every practice problem we did for module 1, 2, 3. So the exam is not going to be any different.
Thank you so much.
Good.
Professor, how many questions on the
I don't know, honestly, I don't know, but for sure it would be good, it would be fair and reasonable for the amount of time I'm going to give you. Okay.
Thank you.
Yeah. Any other question, guys?
And the videos that we're going to watch today, it's not in the exam.
Nope.
No, they are for module 4, they are not in the exam. And I will extend the deadline. I gave you guys till 6 p.m. I'll make it till midnight tomorrow because I thought we'd probably end this at 7, but it probably took the whole class time. But so I'll give you guys for the submission of the quiz tomorrow. I gave you till 6 p.m. I'll give it to you till tomorrow night to watch the 2 videos and do the quiz and get ready for the exam next week. Okay.
Thank you.
Thank you.
Goodbye.
Goodbye.
Take care.
Thank you.
Bye.
Wait, so you changed the time for the quiz?
No, the time? No, it's in the class time.
Okay. No, for the quiz tomorrow.
Oh yeah, because my plan was to finish these questions by 7 and then you guys have the next hour to do the videos. But since these questions because of all the questions and things, which is absolutely okay. It took pretty much the whole class time. And since it's 9 p.m. and you guys are tired, I give you just a little more time so that you guys can watch the videos and do the quiz. So I give you till midnight tomorrow.
Okay, great. Sounds good. Thank you.
Sure. Good night.
Good night.
Bye.